Chapter 3 of the Soil Inspection Manual deals with very basic soil mechanics. We are going to cover two tests that are used to classify soils, Gradation Analysis and Atterberg Limits tests. And then from that, we are going to move into soil classification using the AASHTO M145 soil classification system. We will talk more about compaction of soils and then provide some very basic soil properties for granular and cohesive soil types. So gradation analysis. This is a soil test that is used to determine the distribution of particle sizes in soils, aggregate, and soil aggregate mixtures. We basically oven or air dry a soil sample to 140 degrees Fahrenheit max, and then that sample is passed through a series of sieves with various sized openings. The material that's retained on each sieve is then weighed back to the original dry sample weight, and then from that data, we can construct what we call a grain size curve. The procedure is outlined in Colorado Procedure CP21. In the geotechnical industry, you will be presented with two main types of gradation analysis testing, two methods. First being ASTM, and the second being AASHTO, and there are some differences between these two methods. ASTM defines gravel as that which is retained on the number 4 sieve. And what we mean by saying number 4, number 10, number 20 sieve is the number designation is an indication of the number of openings across a linear inch on the sieve. So a number 40 sieve will have 40 openings across 1 inch on that sieve size. So again, ASTM will define gravel as that which is retained on the number 4 sieve. AASHTO defines gravel as that which is retained on the number 10 sieve. ASTM has more divisions in their coarse and fine sand fractions than AASHTO does. AASHTO, we only care about that which is retained on the 40 sieve, and our fine sand is that which is retained on the 200 sieve. ASTM has more sand fraction divisions. Both ASTM and AASHTO will define our percent fines, our silt and clay particles, as that which passes our number 200 sieve. So once we conduct a grain size test and we weigh back the material that is retained on each sieve and compare it to the original sample weight, we can then produce a grain size curve as shown. On our x-axis, we have the various sieve openings, and on our y-axis, we will have either percent passing in this case, or sometimes you'll see percent retained. On your exam, you will be presented with a grain size curve similar to what is shown, and you will be asked to derive the percent gravel, percent sand, and percent fines, and perhaps the percentage of some other sieve openings. And we are going to show you how to do that at this point. So we'll start with AASHTO. So again, AASHTO defines our percent gravel as that which is retained on the number 10 sieve. So we find our number 10 sieve on the x-axis. We draw a vertical line down to our grain size curve, and then a horizontal line over to our percent passing axis. So for this example, this sample, we see that we have 30% passing the number 10 sieve. So that means we have 70% retained on the number 10 sieve, or in other words, we have 70% gravel in this soil sample. Next, we will address our fines. Our fines is defined as that material which passes the number 200 sieve. So we find our 200 sieve and we draw a vertical line down to our grain size curve and a horizontal line to our percent passing axis. So now we are interested in what passes the number 200 sieve, and in this example, we have approximately 10 to 11% fines. As long as you are within 2% on your exam of the actual answer, we will give you credit for your result. So we will go with 10% fines in this case. Next is the sand fraction. Basically, it has to add up to be 100%. So we take 70% gravel plus 10% fines and subtract that from 100. So we are left with 20% sand for this sample, as defined by AASHTO. Next, we'll show you ASTM. Again, our percent fines is not going to change. AASHTO and ASTM both define it the same as the material that passes our 200 sieve. ASTM, however, defines gravel differently. It is the material that is retained on the number 4 sieve. So to determine our percent gravel using ASTM, we will find our number 4 sieve, draw a vertical line to our grain size curve, and a horizontal line to our percent passing access. In this case, we have 42% passing the number 4 sieve. So that tells us we have 58% retained on the number 4 sieve, or 58% gravel in the soil sample. And then to get the sand fraction, 58 plus 10 is 68. So we take 100 minus that, and we end up with 32% sand in this sample. You will have to do this procedure on your exam. To run a gradation test, you need enough material, and the amount of material that you need is going to be based on nominal maximum size. This is similar to many of the other soil test procedures where the sample mass required is based on your nominal maximum size. Something that you need to know about CDOT is that we define nominal maximum size for our soil tests different than the way AASHTO defines it. At CDOT, our nominal maximum size is defined as the smallest sieve opening through which the entire amount of specimen passes. So for a gradation test, if you're going to be submitting a soil or an aggregate sample to CDOT, specifically for gradation only, if all of your material would pass the 2-inch sieve and you see particles that would begin to be retained on the 1.5-inch sieve, that's an indication that our nominal maximum size is 2 inches. To run a gradation test, we would need at least 16.5 pounds or 7,500 grams of material. These sample masses and nominal maximum sizes are for primarily aggregate materials. If we're dealing with soil, primarily material that passes the number 4 sieve, then we simply are going to want a minimum of 500 grams or 1.1 pounds of material just to run a gradation test. The next test that we're going to use to classify soils is referred to as the Atterberg Limits tests. So the Atterberg Limits, these define the range in moisture content where a soil will behave as a plastic. And there are 2 tests that we are concerned with. The liquid limit test, AASHTO T89, and the plastic limit test, AASHTO T90. Both of these test procedures will be shown to you, demonstrated, and described in a separate video recording. Once we have the liquid limit and the plastic limit derived from these 2 tests, we can then determine our plasticity index of our soil, and that is our liquid limit value minus our plastic limit value. To show you what this means, basically, if we have a soil that's dry, it's too dry to roll into balls or threads, it crumbles, breaks, produces dust, and we then begin to increase our moisture content of that soil. Once we add enough moisture to that soil, we will achieve a moisture content where we can then begin to roll that soil into balls, into threads. It'll begin to stick together. Once that moisture content is achieved, that is approximately our plastic limit moisture content. We then continue to increase the moisture content of that soil, and we will be able to continue to roll it into balls and threads up to a point. And once we reach a point where the soil begins to behave as a liquid, we can no longer roll it, it smears, or in the field during construction, that soil will pump, rut, and deform under loading. Then we have achieved approximately our liquid limit moisture content. And then this range of moisture content where our soil behaves as a plastic and we can roll it, we can form it into balls and threads and ribbons, that range in moisture content is referred to as our plasticity index. So soils with a higher clay content, you can add more and more moisture to them and they will exhibit plasticity, and they will not begin to behave as a liquid until they have a much higher moisture content to them. Soils with lower clay content will have lower liquid limits and lower plasticity indices. If a soil does not have any clay in it whatsoever, we designate that soil as being non-plastic. It will not exhibit any plastic behavior. If an Atterberg Limits test was run on such a soil sample, in a laboratory summary table for the Atterberg Limits data, you will see no value, NV, in the liquid limit and plastic limit data columns, and NP non-plastic and the plasticity index data. When you do calculate Atterberg limits, again, these are simply moisture contents, but they are rounded to a whole number. So once we have a gradation analysis conducted and Atterberg limits testing conducted on a soil sample, we can then classify the soil using the AASHTO M145 soil classification system. This system classifies soils into 8 major groups based on grain size distribution and Atterberg limits, A1 through A8. The sieves that we are going to use are the 10, the 40, and the 200, but we are primarily concerned with the 200 sieve. And then we need our liquid limit and plasticity index of the soils. This is the AASHTO 145 soil classification system. We see we have A1s, A2s, A3, A4, 5, 6, and A7. A8s are not shown. Basically, an A8 is any of these soil types that contains 15% or more organic materials. Those soils that are A8s or that have organics in them are not suitable for embankment construction, and they are not suitable to be left in embankment foundation materials. So as we look at this table, we see our sieve data here, gradation results, percent passing, the number 10, number 40, and number 200 sieve. And we are primarily concerned with what passes the number 200 sieve. And we see minimum and maximum values for the various AASHTO classifications for the amount of material that can retain or pass the number 200 sieve. And then we go to our Atterberg limits data, liquid limit and plasticity index. And again, minimum and maximum values for the various AASHTO classifications for both liquid limit and plasticity indices. And then at the bottom here, just very generalized descriptions of these soils. As we go from left to right on the AASHTO table, we go from more granular soils to fine soils containing more fines. And then within the various subgroups of soils, from A24 to A27, we go from low plasticity soils to higher plasticity soils. And then our A4s to A7s, again, low plasticity to high plasticity. And then a various description of the rating of these materials as subgrade material. So our A1 soils, these are granular soils, sands and gravels with less than 25% fines, non-plastic or very low plasticity. The maximum plasticity index is 6. So with a PI of that value, we would refer to those soils as being silty. A2 soils, these are also granular soils, sands and gravels with up to 35% fines. The fines can be non-plastic or silty, or they can range up to a higher plasticity. Those would be our A26s and A27s. A3 is a fairly unique soil. Think of a fine beach sand. So it's a fine sand without any plasticity. A4s and 5s, now we are dealing with soils that have more than 35% fines. The A4s and 5s would be considered silty soils. They have a lower plasticity. A6s and 7s are our more clayey soils with more than 35% fines and have a medium to high plasticity. And again, the A8s are any of these soil types that contain 15% or more organic matter. So on your exam, you are going to be provided with gradation data and Atterberg limits data, and you will have to use the AASHTO M145 soil classification to derive an AASHTO soil type. We're going to give you an example now. And you have another example in Appendix 2 of your soil inspection manual. We have our liquid limit of 32, our plasticity index of 16, percent passing our number 10, number 40, and our number 200 sieve. What we are primarily concerned with to derive an AASHTO classification is what passes the 200 sieve. So this process is basically a process of elimination. You can go in whatever order you wish, but for this example, I'm going to start with my 200 sieve. This soil sample only has about 32% passing at 200 sieve. So right off the bat, I can eliminate all 4 of these soil types because these require at least 36% passing our 200 sieve. Next, we are going to look at our Atterberg limits. We have some plasticity to this soil. It has a PI of 16 and a liquid limit of 32. So we can eliminate our non-plastic soil and eliminate our A1 soil that only allows a plasticity index up to 6. So now we are left with one of these A2 designations, A24 through A27. So again, if we look at our plasticity index and our liquid limit values, both of these soils allow us a liquid limit up to 40, so that matches. An A24 only allows a plasticity index up to 16. So now we are left with an A26 soil. This criteria is met for our percent fines in our liquid limit and Atterberg in our plasticity index data. So in addition to determining an AASHTO group number, the classification goes a bit further, and we are going to determine a partial group index number for our soil. Partial group index is a number that is placed in parentheses after an AASHTO group number. So an example, an A6 with a partial group index of 5. What that number is, it's an indication of the percent fines a soil contains, the plasticity of those fines, and the quality of the soil as a subgrade material. To determine the partial group index, there are equations that you use. The liquid limit partial group number is going to be determined. The plasticity index partial group number is going to be determined. Those two values will be added together and rounded to a whole number to get your partial group index. We're going to go through an example with you. And again, you will have to do this on your exam. And an example is also provided in Appendix 2 of your soil inspection manual. So to determine the liquid limit partial group number, we use this equation, where F is your percent fines, the percent passing the number 200 sieve, and LL is your liquid limit of that soil, and again, rounded to a whole number. So you plug in your percent fines and your liquid limit into this equation. You run through the correct order of operations to calculate your liquid limit partial group number. Oh, note, if the percent passing the 200 sieve is less than or equal to 35, the liquid limit partial group number automatically becomes 0, and you do not need to go through the entire equation. The plasticity index partial group number is given by this equation. Again, F is the percent fines passing the number 200 sieve. PI is the plasticity index of your soil, again rounded to a whole number. So for our example now, in that soil that we classified as an A26, we had percent passing the 200 sieve 39.9, liquid limit of 32, and a plasticity index of 16. We are going to determine the partial group index of this soil. So we start with the liquid limit partial group equation. We plug in 39.9 for the percent fines and 32 for the liquid limit. We go through the correct order of operations, and we will derive a liquid limit partial group number of 0.7. For the plasticity index partial group number, again, we will plug in 39.9 for the percent fines, 16 for the plasticity index. We go through the correct order of operations, and we will derive the plasticity index partial group number of 1.49. So we have 0.78 and 1.49. We then add these two values together to get a partial group index, and we round it to a whole number. So our completed soil classification is A26 with a partial group index of 2. Compaction now. So basically what compaction is, and why we are compacting soils, it is densification of soil by removal of air voids. What this does is it increases the strength of foundation and embankment soils. It decreases the likelihood of post-construction settlement, and it increases the long-term stability and performance of the roadway. The tests that you run to determine compaction in the field and to determine optimum moisture and maximum dry density are AASHTO T99, standard Proctor, and AASHTO T180, modified Proctor. So to think of compaction, removal of air voids, imagine in your mind a container full of soil that has some moisture to it. So what this container has in it, or the material, we have solid soil particles, and then we have void space in between those soil particles. Because the soil has some moisture to it, some of that void space is partially filled with water. So when we are talking about compacting soils and removing air voids, basically what we are doing is we are compressing that soil and causing the air to squeeze out of the void space. What we need to know in the field and what we need to be aware of in the field is a term that we are going to refer to as zero air voids density. So if we go to our container of soil that has void space partially filled with water and partially filled with air, if we were to compact that unsaturated soil specimen to a point where all of the air is gone and we are only left with moisture completely filling the void spaces, that is what we refer to as the zero air voids density. So zero air voids density is the dry density obtained at various moisture contents if soil could be compacted to eliminate all of the air voids present. In other words, all of the voids are filled completely with moisture. What you need to know in the field and during construction is it is not possible to achieve zero air voids density by compacting an unsaturated soil with conventional construction equipment. And to calculate our zero air voids density, what we need is specific gravity of the soil particles and the moisture content of the soil. So we have shown here a Proctor curve. We have a standard Proctor and a modified Proctor curve shown. Standard Proctor or T99. Again, these are compacted with less compactive effort, a higher moisture content. So if we have the same soil type, compact one specimen at standard effort and one specimen at modified effort, standard Proctor will be a wetter Proctor with a lower dry density, a lower maximum dry density. And the modified Proctor of that same soil specimen will be a lower moisture content, a drier Proctor with a higher maximum dry density. And then we see our zero air voids curve. So again, this curve is developed based on the equation that we are going to see on the next slide, where we need specific gravity of the soil particles at various moisture contents, and we construct a zero air voids curve to go along with our Proctors. What you need to know in the field when you have your Proctor curves with you and a zero air voids curve shown on that Proctor curve, the maximum dry density should never fall above the zero air voids curve. So in other words, when you are taking a nuclear density test to test compaction in the field, if you derive a dry density of the field material from your nuke density test that exceeds your zero air voids density, then that is an indication to you that you are using the wrong Proctor. You need to either find a more suitable Proctor that matches your soil material or perhaps develop a new Proctor curve. In addition, the dry density that you determine in the field should never be more than 5% above the laboratory determined maximum dry density for that soil. So if you start seeing Proctor or nuclear density test results that show 105, 106% compaction when you're comparing to your Proctor, again, that is an indication to you that you are using an inappropriate Proctor curve for that soil, and you need to develop a new Proctor curve or find one that more closely resembles the soils that you are having in the field. So always verify your soil's Proctor curve if the results are questionable. So now to calculate zero air voids density, this is provided to you in Appendix 3 of your soil inspection manual, and you will be expected to do this on your exam. We need the specific gravity of your soil particles. This 62.4 value is the unit weight of water, and we determine this at various moisture contents to develop that zero air voids curve. So if we want to determine zero air voids of a soil at 11.5% moisture content, and we determine the soil specific gravity is 2.65, we simply plug specific gravity into the equation where it belongs and the moisture content where it belongs. We run through the correct order of operations, and we would calculate a zero air voids density of 126.7 pounds per cubic foot at that specific moisture content, 11.5%. So if we were to run a nuclear density test in the field on a soil that happened to be at a moisture content of 11.5%, and we derived a dry density of, say, 128 pounds per cubic foot, that would immediately tell us that we are using the wrong Proctor curve, because we cannot have a dry density in the field that exceeds our zero air voids density, and we would have to develop a new Proctor curve for that material. The last thing we're going to cover is some very basic soil properties for granular and cohesive soils. So our granular soils, sands and gravels primarily, these are going to be non-cohesive, generally no stickiness, no plasticity. The particles will be visible to the naked eye. Soils that are primarily composed of sand and gravel have high strength, so they are stable, and we can construct those embankments at steeper slope angles. They have high porosity, so they drain well and they do not hold water. Because they're highly permeable, it is much easier to uniformly moisture condition them and then construct them into engineered fills. These soils, when in the foundation of an embankment, are not prone to post-construction settlement. Cohesive soils, on the other hand, silts and clays, those fines, silts and clays, when you're talking about soil, these are the materials that when you have a soil sample in your hand, they make that soil appear, quote, dirty. Or when you smear that soil in your hands, it is the fines, the silt and clay particles that leave that stain on your skin. So these individual particles are not visible to the naked eye. You need a microscope to see silt and clay particles. They are lower strength, so fills that are derived primarily of cohesive soils must be constructed at shallower slope angles. Silty soils especially are prone to erosion with rainfall and near flowing water. Silt and clay soils, they do not drain well, they have low permeability and have a tendency to hold water, which reduces stability. So silt and clay soils are susceptible to post-construction instability and settlement. Because they have a low permeability, they are more difficult to work with to achieve adequate compaction. They are more difficult to uniformly moisture condition. So this concludes Chapter 3 of the Soil Inspection Manual in this part of the presentation. The next chapter will discuss CDOT's earthworks.